Okay.
Yes, now
Very
recording
good.
starts.
Very good. Okay, so here, share the screen. Let me know, please, if it's not working, but it should be okay, I believe.
I think it's okay.
Seems okay. Okay, good. Here we go. We had a little chat. We had a pre-chat on Saturday, and we sort of, I could see that you know what is the crux, at least to some degree, what is the crux of the great success? What is the essence? Where the strength lies of the standard model of all the interactions that matter. So standard model, right, is the theory of, let me write here, of all particle interactions, elementary particle, of course. And I say all. So there is the electromagnetic, there is weak, as you know. And we'll chat a little bit of each of them. To some degree, I always start from scratch, as if you don't know, but of course you know. And then, of course, there is gravity. And yet I won't say a word about gravity because gravity does not matter. Matter gravitates, of course, matter, the only force that you and I really see is that matter does gravitate. All matter gravitates. Not just matter, even nothing gravitates, even vacuum gravitates, right? The beauty of Einstein theory of gravity is that its messengers that presumably exist, or the way it acts, the graviton or the way it acts, is that it couples to everything that carries energy. In principle, even vacuum can carry energy. We'll comment on that. Matter gravitates, but gravity does not matter. Why doesn't gravity matter in the world of elementary particle? Who can tell me?
Because compared to the other forces, gravity is very weak.
It's very weak, right? You know how weak when you say very weak, roughly. So if I write the electromagnetic potential, for example, static potential, that I would write e to the minus, say, alpha over r, where alpha is the celebrated electromagnetic constant, e squared over 4 pi, which is roughly 1 over 100. We'll talk about the precise numbers, but you know that it's order 1 over 100. And it's dimensionless in my and yours crazy units that we like to have. We particle physicists, h bar equals c equal 1. The gravitational static potential, if I write static, would be minus g Newton m1 between two particles of masses m1 and m2 and r. And even if I take a rather heavy elementary particle like a proton, well, it's not elementary. I should better be careful, right? It's a composed, well, almost elementary, but just to understand between two protons, it will force will be very small. Why? Because g Newton in our units, let me just write here. We often like to write that g Newton is 1 over m Planck. You can put a factor of 8 pi. Let me just write like this. Often there is a factor. Just to emphasize the right dimension. And who can tell me how big m Planck is?
10 to the 19.
Right, 10 to the 19 in the proton mass unit. We said we like to use always the basic unit that we are all made for. So if in the units of proton mass, for example, the force between two protons sorry, what in the world am I writing? And proton is GeV. I will have the force. Gravitational force is some 36 orders of magnitude, right? V gravitational over V electromagnetic is roughly 10 to the minus 36, which is 0. Most of the time, you and I will work what we call the tree level when I ignore the effects even of 1 over 100, let alone something which is 30 orders of magnitude smaller. So I don't have to worry about gravity, which is a beautiful theory and whose understanding is maybe one of the most profound tasks of particle physics. And it's just worth saying here, it is often said that the Einstein theory, right? Here we know, I just wrote a Newtonian potential. The true theory, of course, of gravity is the Einstein theory, which has been argued for decades. And I can see that most of you have fallen into that trap. The people have claimed endlessly that gravity has to be changed because it doesn't work as a quantum theory. And someone would add one field and call it Browns-Dicke. Some other person would add two fields. Okay, most of this was a childish game in which you keep the same trouble that gravity apparently has, to the extraordinary suggestion that you should have infinitely many particles, infinitely many particles. That's called the string theory. You organize them as the excitations of the strings. We claimed that this could solve the problem. Of course, it didn't. It did absolutely no improvement on the theory of gravity. And there are various directions taken there. What has emerged in recent years, this is the last time I will speak seriously about gravity. They started with the work of Hopf some years ago, and then Dwali in Germany. Is the argument, very interesting argument, that Einstein theory could be right. Remarkable thing. At energies, it's supposed to fail when you go to the energies much bigger than Planck scale. But actually, there is a fantastic, interesting, spectacular possibility that it could work. It has to do with the beauty of the black hole physics. And if you want to hear more, you will sometimes ask me about it. Oh, by the way, before I go on, let's choose a day for office hours. I want to make sure you can contact me whenever you have problems and you want to talk to me, but let's set a day where we could have guaranteed some afternoon that I'm around office hours. Is there a day, afternoon, that you people find preferable? You can write on chat. Maybe we should start like that. You write on chat and then we'll talk in the break or maybe after the lecture. So what I need to find the best time for office hours, at least once a week, we will meet. If you come, if you wish. So that the questions that you didn't prepare or during the lectures that come up afterwards, you can ask me. Well, you can ask any questions, or even the things that I'm not really teaching at the moment, but I touch upon the things that are staying in the lectures, okay? So at the moment, I'm not really teaching this. I'm just saying that there is a beautiful possibility, which you will learn, you guys. I don't know how many of you seriously want to do physics, really do physics. Understanding the phenomena. One of the reasons that people change the theories very often, it's much easier to change a theory than to really get to the nitty-gritty of the theory. That's a hard work, understanding the theory. And I'll start in a few minutes, okay? Just keep this in mind, this interesting remark I'm making that has emerged in recent years. But since I'm here to speak about the physics as a natural philosophy, I want to speak about the physics that describes phenomena that we can observe, that we are observing first, which is a standard model, and then I will whet your imagination by talking of the things that could be observed in the near future, because at least in one aspect, standard model is not complete. I will not speak about gravity because the effects are obviously too small, as beautiful as the subject is. I will concentrate mostly on electromagnetic and weak interaction because this is where the developments of perturbative field theory lie, which is much easier to understand. So this will be the central part. And of course, we will spend some time to at least assess the essence of strong interactions. Okay. So in a sense, I'm yet about to start. I'm still chatting. I don't know if you want to ask something here before I move on the, please feel free to interrupt. What else do I want to say here? I guess nothing. You knew on Saturday evening, most of you, that the crucial thing here, however, in the standard model is the central issue, central to all these forces. Now that I don't have to speak about gravity, is the gauge principle, if you wish, gauge symmetry, it's often said. The word is not really right. It's not the symmetry, the gauge principle, let's say. Which what I mean by this is that each of these interaction is based on a gauged group. Electromagnetic is U1, as you know, right? Then the weak is which gauge group? SU2. And strong is SU3. So for us to sort of grasp the crucial thing, let us start with electromagnetic interaction. Just because it's simple. In other words, what I want to do, I want to start with QED. It captures almost all the fundamental properties of everything that we follow in the rest of the course, almost. So please, it is crucial, you know, whatever things that we are going to do in the future, it is somehow extremely important that you master the U1 aspect. Once you do that, the rest is just some more complicated group theory, which lures, of course, to another deep and interesting physics, but the issue, the crux is the same. And the Lagrangian is QED, as I'm sure you know. Look, at the classical level, you will write it as the Maxwell Lagrangian 1/4 F mu nu, F mu nu, the way we normalize the kinetic energy, the propagation of photon minus the current of the photon, interaction of the photon with the electromagnetic current. This you would write even at the classical level, where F mu nu, of course, is the anti-symmetric tensor of electric and magnetic field, right? EI is F0I, and there is a magnetic field, which is the space component only, epsilon ijk, bjk. Maybe there is a factor of half here, I believe. Normalization, okay. The thing that, of course, characterizes the fundamental quantum field theory aspect of elementary particle interaction is the form of the current. It is simply psi bar corresponding to the fermion F, gamma mu, Q electromagnetic, phi F, where phi F is the phase function, a field, better to say, corresponding to the fermion F, and we sum over all the fermions. The beauty of QED day is that interaction is universal. All the charged fermions interact the same way with the photon. And the Q electromagnetic, I will often forget, or I maybe won't care to write the index, so I may call it Q, is just a collection of charges. It's a diagonal matrix in the way we are writing. that sort of takes care of the values of the charges. So there'll be charge of the electron, charge of the up quark, charge of the outward, whoever has a charge is here. And whose charges apparently you know. I will make sure to remind you. So if I know your charge, I know how you couple to the photon. This is the, and to this, of course, QED, one has to add something else. There is also the Dirac piece here, because once I have that interaction, I need the kinetic energy and the mass term. And of course, this is how it all started. The modern particle physics starts arguably with the extraordinary work of Dirac. This all you know. I hope I'm boring you today. And maybe I should stop writing, there is a sum over all the, I'm sorry, let me write this better. The Dirac Lagrangian is the sum of all fermions. I should stop writing the sum. This is kind of obvious, right? This is the Lagrangian that we all know or love, where, of course, gamma matrices, let's really stick to the basics today, satisfies the Dirac anti-commutation relations, where G mu nu, let me specify it immediately, the metric tensor, I may sometimes call it eta mu nu. If I were to say anything about gravity, then G mu nu would be reserved for the situation when we include gravity, but in this case, it does not matter. And this is again diagonal matrix. 1, minus 1, minus 1, minus 1. I hope we are using the same metric. I, what is the point of gamma matrices? They give us the generators of Lorentz transformations, the commutators do the job of generating the Lorentz transformation on the field that we call phi f, which is a spinor, right? This is Lorentz acting on spinors. It's important to remember, we'll come back to that. This will be the crucial thing later, and the moment not so important. I can also introduce gamma 5, which is defined as gamma 5 square is 1. Notice that the sign of gamma 5 has no mixed physical meaning. Please. Because sometimes there is this thing that we'll talk about whether I write 1 or plus minus gamma 5. It has no physical meaning. I come back to that. It's defined as gamma 5 square is 1. Gamma 5 anti-commutes with gamma mu. In other words, it's not that only there are 4 of them. There are actually 5 of them that I can introduce. It's not used to build the generator, and it actually commutes with the generators of the Lorentz group. Because it commutes, you introduce the projectors, which I will call 1 plus minus. It may differ from, oh, I have to send you, or you have this with my notes, in which I may have even used minus. It doesn't matter. You should be used to the fact that it's completely relevant whether I use plus or minus in the definition of left. Okay, it's a pure convention because gamma 5 itself is not defined up to a sign. These are projectors, obviously, because gamma 5 square is 1. In other words, L square is L, R square is R, and left, right is 0. That's one thing that we'll need later. I can as well give you now the gamma matrices, okay, to date. And as usual, we will have always a mixture of the technical part and which some days may be boring, but it's important. And the physics that follows. So the my gamma mu matrices, let me use them here, are off diagonal. With and sigma mu plus minus is 1 plus or minus sigma I. It's just a notation for kind of 4-component, if you wish, version of Pauli matrices. Sigma I is Pauli that you have to know in your sleep. So in other words, all the gamma 4 matrices are diagonal. Let's be specific just to be sure that you got it right. Gamma 0, 0, 1, 1, 0, and gamma I is 0 sigma I minus sigma I 0. In this, with this convention, gamma 5 that I will choose will have this form. 1, it is diagonal, and I normalize it to be 1, 0. Okay. So I'm not sure. Let's check each of you. I think gamma 5 is minus. Gamma 0. It's not so important. What is important is this form. This is crucial. In relativistic quantum field, diagonal gamma 5 is much more useful to see what is going on. Remember, in non-relativistic physics, you inverse gamma 0 and gamma 5. You take gamma 0 to be diagonal because that will give you large and small components of your non-relativistic spinner, whereas in our case, we will be dealing with very high energetic particles. You and I want to be able to discuss what is happening, say, at LHC. At LHC, basically every particle is massless, right? Massless particle has 0 mass, but particles with a very small mass. So when I say small mass, what do I mean by small mass? This is sort of, it will be clear from the context, not by itself. If it is if it is an experiment that I'm talking about, that of course means that mass is much smaller than energy. But I may speak of a static particle. If it is static, then I will often mean that the mass is much smaller than mass of the proton. And so on. It should be clear from the context. So, oh, by the way, we should say that then left projector is then 1, 0, 0, 0. And R projector is 0, 0, 0, 1. So what do they do? If I write, this is a convenient way of writing. The 4-component Dirac spinner, as you know, can then be written as UL, UR, so that L psi is U0 and R psi is 0V. Every time you see a 4-component spinner, the left-handed guy is on the top and the right-handed guy is at the bottom. Doesn't matter how you nominated it, what you do, okay, that will be the definition of left and right. There is a first exercise. This could be the homework. I have to decide on the first homework in a day or two. From here, I won't derive it here. But please, in order to see whether you are able to follow this, this is something you should know. You should show that ULR transforms as e to the I eta I. No, I'm sorry, I rushed. I'm rushing ahead of myself. Not yet, I'm sorry. Here I forgot to say, this is very important. What do I mean by spinor? I forget to say, of course. Spinor psi transform when I say Lorentz transformation as psi, where S, Lorentz transformation is e to the I, theta ij, sigma ij. This, of course, is very important. We have 6 generator of Lorentz group, theta ij. Since sigma ij are anti-symmetric, there are 6 of them. We have six kind of 6 generators. I should write like this. I really meant here. Here there are 6 generators. And theta characterize these transformations. Why there are 6 generators? There are 3 rotations and 3 boosts, as you know. Okay, what else? Okay, you can then show, please, this is your task, that UL are the 2 component pieces of the 4-component wave function transform as e to the I sigma I over 2 Pauli matrices theta I plus I, we can say phi I plus or minus, not plus, but plus or minus UL. In other words, the 2 component spinors transforms almost the same. Is it the same under theta I? What do theta I's? What do they correspond to? Theta I's? These 3 parameters.
Rotations.
These are rotations. So obviously, any spinor, any 2-component spinor, of course, it's a spinor and the rotation, so they have to transform the same way. They, however, have an opposite transformation clear. If this was a rotation, this is a boost. This is the name left and right. If one guy goes left, the other guy wants to go right. This is what you have to have in your fingers. The standard model course, this is what has to emerge if it's not already there. They're equally familiar at any moment of day or night with the 4-component notation of Dirac, which is extremely useful when I talk about QED, but totally useless if I want to talk about weak interactions. Okay, therefore I have to be able to master both of these to be right. Think of the 4-component spinors, but at the same time that you can quickly untangle the 4-component spinor into these 2-component pieces. What Dirac just does with his wave function field. So this is just bookkeeping. This is not a fundamental quantity, the Dirac spinor. The fundamental quantity is, of course, irreducible components, which on their own would never change, but remain the same. In other words, when I write the Dirac Lagrangian, which I wrote as I psi bar gamma mu d mu phi minus m psi bar psi, this is actually I psi L bar gamma mu d mu psi L plus I psi R bar gamma mu d mu psi R, where psi L was I written before. Once again, that you see it is just the left-handed part, The upper component, psi r, is just the right-handed part of the four-component wave function. So the kinetic energy, of course, it tells you if you have a particle which is propagating on its own, the kinetic energy stays. It's an irreducible component which is true to itself. Therefore, a left-handed piece moves by itself, not transforms. I'm sorry. The left-handed kinetic energy is separated from the right-handed. If they had mass, you would even never know that there are two of them. It is the mass term, of course, which mixes the two, which I can write like this. Psi bar is psi L bar, psi r. It can be written in the two-component form. This is I, UL dagger, sigma mu minus, I believe. Who's going to check for me while I'm writing? What will be? It's off diagonal. Let me think, UL. I leave it for you. I think I'm writing correct. No, I'm not sure whether I'm writing the upper component. I think it's true, but I'd love you to check. I will on purpose. I may sometimes make a mistake on purpose. I'll make a lot of mistakes which are not on purpose. Sometimes I may write something wrong on purpose just to see if you are not, being awake and following me, and then later checking. And sometimes I deliberately leave you for you guys. Some computations we will do, many of them will leave to you guys. I'll come back and check this, but where was the gamma zero? Was 0 sigma mu plus sigma mu minus? I think this is correct. I put a question mark here. Means whenever you see a question mark, if you ever go over my notes, it's telling you that I didn't want to do it, I left it for you. By the way, it's a convention. In the end, if I made a mistake, well, you will correct it because it's just a convention how I've chosen my gamma matrix. I should stick to my convention though. Okay, if I talk only about QED, I make this digression so that I can prepare myself for the future. But if I want to talk about QED, I don't even have to beg you back with left and right, because this is how the photon interacts. Photon doesn't care whether you are left-handed or right-handed, it couples equally to you. Just like the kinetic energy, notice that the current would couple equally to left and right. The current has the similar form as the kinetic energy, and it breaks into left and right separately, okay? What we say, in other words, the interaction, the current, the electromagnetic current, J mu, electromagnetic, which is psi bar, gamma mu q psi, is psi L, gamma mu q psi L, plus psi r, gamma mu q psi r. It is left-right symmetric, manifestly, and trivially, obviously, just because the kinetic energy is, and it has the same form, gamma mu. There is a left-right symmetry here. Left-right symmetry, of course, is what we call parity. We'll talk a lot about it. I'll start from scratch there. And this is why Dirac never paid attention to the chirality, to the handedness of particles. We'll have to do the opposite from him, because we'll spend a lot of time talking about the weak interactions. That's the fun part. Questions here? It's all basics, okay. I'm glad that there are no questions. That's presumably it's all well known and clear. once again. It's just, this was just a digression to give you a sense. I've done all of this, that the D-spinner that I wrote like this, the crucial thing is, instead of looking up, once again, I have a QED Lagrangian that I can now write more coherently. I'll just write for one fermionic field. I wrote psi f before, I can just write psi. Let me note some is, I can write like this, gamma mu d mu, as you know, covariant derivative. There is a mass term. It's an extremely simple universal theory. This is the beauty of QED with the Maxwell electromagnetic interaction, where the covariant derivative is simply a nice bookkeeping of the kinetic energy and the interaction of the photon. This is an extraordinary success. This had emerged in the 50s, right? The late 40s and especially in the 50s, it emerged through the work of Schwinger, Tomonaga, Feynman, and Dyson, but the first three of them built the theory. Dyson completed it. You could describe any electromagnetic process, whether it's annihilation, whether it's a scattering, to an extraordinary precision that kept growing, and today is 1 in billion, basically, okay. Extraordinary effects of perturbative. This is a perturbative theory, perturbative field theory that we called quantum field theory, whose expansion parameter, once again, alpha is e squared over 4 pi. And the number I'm not writing deliberately, it's a number over the 100. You will see why I'm not writing deliberately precise number. What else? Well, here comes the crux thing, which is characterizing the theory, is the fact that it's invariant under the following transformation. Phi goes into e to the I, some theta of x, let's say, psi. This has nothing to do with Lorentz. Of course, it's just a times q. Sorry. Q is Q electromagnetic. I may not write every time. Forgive me if I don't, because it becomes heavy. As long as A mu also transforms. This is the what we call the gauge symmetry. I put quotation marks for symmetry because, strictly speaking, if you think about that, it's not really a symmetry transformation in the following sense. Okay, here comes the crux that you know, but let me remind you. It all starts with the fact that I had a theory when I write the Dirac-Lagrangian, when I write the Dirac-Lagrangian. Dirac-Lagrangian is invariant under phi goes into e to the I theta phi. Psi is a constant. And then Eminator teaches you, as you know, when this is true, there will be a conserved current. And J mu proportional psi bar gamma mu psi. The coefficient is irrelevant. Eminator doesn't care which coefficient you put. There will be this conserved current that I'm sure all of you know how to derive. This is a genuine symmetry transformation, global symmetry transformation. In other words, we have a global, this is a global transformation property. Theta is a constant here. Let me write more clearly. Global, I should write here when I say that it's global. Theta is a constant. This is very important. And this gives you a conserved current. Once I promote theta as a function of x, there is nothing more emerges. There is no new current that emerges. Really, the reason that there is this gauge, so-called symmetry, lies here. We call it often gauge redundancy. Which, as you know, is there because for me, since I want to keep Lorentz symmetry transparent, I want to write the theory in a Lorentz covariant manner so that the results are easily Lorentz invariant. I'm working with a 4-component field A mu, but that of course corresponds to nothing. That's not a physical field. In this theory, so once I make theta as a function of x, it will just take care of the fact that A mu has 4 degrees of freedom. And how many are physical? Only 2. Why? Because in this theory, manifestly the way I wrote, photon is massless. And then, as you know, when the particle is massless, there is no mass to talk about, and you cannot talk about spin, right? The only physical quantity is, what is the only physical quantity for a massless particle, whether it's a, fermion or gauge boson, it's irrelevant, it's helicity. I cannot speak about, which is a projection of spin on the direction of motion. This, of course, is the only characteristic, and this, what would be a spin 1 particle, is plus or minus 1. So I have actually 2 degrees of freedom, and if I were to work with these 2 degrees of freedom, I would find no gauge symmetry, no redundancy. But since I like to keep Lorentz symmetry, obviously they cannot be all physical, and therefore there must be some set of equations that show that some components are redundant. This is what we mean by gauge symmetry. It also means something that I already mentioned on Saturday night for those of you that were there, that this is kind of natural. If I ask that I'm using one phase here, and you are choosing a completely different phase at your place, and we are not together, we are now in completely different places. Obviously, someone is going to connect us. That messenger, that's what a photon does. Photon ensures that you and I can change the phases of the same Lagrangian as we like at different space-time points. So a mu, which is a messenger of electromagnetic force, it's also a messenger, if you wish, of this gauge transformation that I want to take. Theta equal theta of x. This sort of captures the essence of the, and it plays a fundamental role. When you quantize the theory and you work out the scattering amplitudes and you do the perturbative expansion, as you know, of, so how does it work? Well, I say the following, Feynman total. If, for example, electron comes, what the electron can do while moving, it can emit a photon, and someone else comes, maybe it's a muon, maybe it's an electron, can absorb that photon, right? So the thing is that electron, the beauty of QED, electron stays electron, you cannot change electron into a muon, photon keeps the flavor, we say, E, mu, and so on, we call this flavor in the standard model language. This is my photon, which is propagating. By the way, I will often do this that I call photon gamma. It traditionally was gamma radiation. Okay, this is how it works to provide me an electromagnetic force. And really simple form, I can describe all the processes we said. And we do it as a perturbative expansion. You see, every time we put the coupling constant, I should have chosen a muon. Okay, let me put it here. E here, E stands for the coupling, not for the electron. You see the problem of the, okay, or you can tell me, why don't you write psi electron to be correct here? Okay, maybe once I do that, I will often call the wave function by the, better to say the field, by the name. So in most of the course, if I write a muon, if you see sometimes it will stand for the field of the muon. An electron may stand for the field of the electron and not the electromagnetic coupling. You know, there can always be confusion, but you'll know this. And I also like to do loops. I may say, okay, there is an electron. Let me draw it a little differently that it's easier. I can exchange two photons in the same scattering. And you see, I'm getting an expansion. I hope I'm still boring you. Because now it's not of the order E squared, but it's of order E to the fourth, right? Here, this amplitude was of order alpha, E squared. This one will be of order alpha squared and so on. You see how lucky we are? What makes QD really work? That the expansion parameter is not E. Remember, the coupling itself, the gauge coupling is not small. Just remember, when alpha squared is of order 1/100, E is of order 1/3, roughly, maybe even a little bigger. It's not small at all. It's just that we are lucky that the expansion parameter is E squared over 4 pi. It makes all the difference in the world. There is immediately a factor 1/10 coming from 4 pi. So this is one central aspect of the QED that I will borrow on. I will often, mix the logic, the presentation, the theoretical and mathematical part with the historical one. I told you this on Saturday. I want you to appreciate how this ideas developed, how in the beginning you are completely in the dark. I want you to understand that this simple understanding that we get comes with a lot of blood, sweat, and tears, and a lot of confusion. And I will later, follow this principle when I want to build the weak interaction part, which you may know, but I want to make sure that we are building it from scratch so that you participate in the process and not just learn it by reading. Okay. So this is sort of, look, let's do the following. Since I want to move to something very else, I'm actually going to suggest that we take the break now. Let's make it today 10 minutes. I got up very late. I need 10 minutes to prepare my coffee. But before I do that, I want to see whether there is an urgent question in this little kind of reminder, if you wish. So please, if you have any question here, you don't feel bad because I'm not really teaching you. I'm here making a collection of making a series of statements on something that you have been taught. But still, maybe there was something that still remained a little puzzle or whatever. Okay. You seem to have no questions, so I'll give you 10 minutes. So let's meet at 12:10. If you don't mind, we'll usually have shorter breaks. Let's meet today at 12:09, 12:10. And I don't know if you want to stop and restart the broadcasting or keep it, you decide. Maybe to enjoy the privacy, we can actually stop.
Recording in progress.
Any questions, please? I will be pausing from time to time, encouraging the questions. It's not that I don't know what to say next. I just want to make sure to give you a chance. Now, the way I wrote what was clear, the way I wrote QED and immediately explained that, as you knew, that this is a mixture of left and right, the current, means that QED is left-right symmetric. We said it above. What we didn't say is that really what amounts to a parity transformation, but you know that QED is invariant under parity transformation. So what is parity? Parity is A0 goes into A0, and AI is a vector, A0 is a scalar under this, not a Lorentz scalar, but it's a scalar. And that means that phi goes into gamma 0 phi. This is what parity does. This is manifestly invariant because we had an interaction A mu proportion. In other words, interaction is, let me write more clearly. Interaction is proportional to A mu psi bar gamma mu phi, which is A0. This is kind of trivial, psi bar gamma 0 phi plus AI psi bar gamma phi. It's very easy to see that this is invariant. Obviously, A0 invariant. This piece is invariant by itself. This goes into minus AI. And this obviously goes into minus psi bar gamma I psi. Because gamma 0 and gamma I anti-commute. I don't even have to write it. This has to be in your fingers, not in your mind. But what does it mean that phi goes into gamma 0 psi? So this is parity. That means that UL UR goes into 0 1 1 0 UL UR, which is UR UL. Parity is a left-right symmetry. UL is interchange with UR. This is parity. I will write a bit carelessly. We do that very often. I will often write that psi L, often one writes carelessly, that psi L goes into psi R. This is not true, strictly speaking. The meaning is here. Actually, psi L goes into gamma 0 psi R in order to UL. The meaning is above. But when you see this written, don't feel bad. The author of whoever is making this statement really wants to say that left goes into right, and that must be on the basic, fundamental, two-component, irreducible fields. Okay. Here is the essence of parity. Parity is the symmetry between left and right. And I'm going to talk a lot about parity. I pay particular attention. I want to show you that parity is, and the breakdown of parity is equally important for the success of the standard model as the gauge principle. Okay, people often forget to stress this. That will become clear only towards the end of the course. And the reason I want to emphasize the parity, and the reason I think that everybody should think more about parity, to me it was clear when I started out doing my PhD. This is the first symmetry you see as a child. You look yourself in the mirror and you go crazy. You realize, I remember all my life, when at the age of 4 or 5, I saw myself in the big mirror of my parents' room. And I was puzzled endlessly with this left becoming right. It was one of the most fascinating things I ever seen. And I found it somehow fantastic that 20 years later, I would learn that particle physics or weak interactions or electromagnetic weak interaction, the so-called standard model, is all about this symmetry. And you will see how important it is when we talk about neutrino. Okay, so this is when I want you to pay attention. And this is why we have to learn the language of left and right so well, because of this thing. There is another left-right symmetry. This is interesting. Parity is a left-right symmetry, but it's not the only left-right symmetry. There is yet another left-right symmetry. Can someone tell me which it is? This is the essence of the relativistics of Dirac. Which are the transformation? Which are the symmetry, you know, discrete of the Dirac-Lagrangian besides parity? So go back to Dirac. Or even QED. Why do I have to go to Dirac? What other symmetry that you know?
Charge conjugation.
Charge conjugation, yes. I mean, what was really incredible thing that Dirac discovered, right? Why is it such a great work? I mean, for you and I, the work of Dirac is more important than the work of Einstein, if you want to do particle physics, and not ADS, CFT, or whatever, that makes you think that the work of Maldacena is more important than the work of Einstein. This is what drives me crazy, that so many of you want to prefer the manipulations which have nothing to do with reality to reality itself. I will be making strength statements which will be broadcasted, and I do it on purpose. I find it very disturbing that modern particle physics is going away from its own study. Okay, you have to study the phenomena that are there. Once you understand them deeply and work on them, then move away. Now, charge conjugation, because what Dirac discovers is amazing. He writes this equation for a fast-moving electron, and he finds there is spin inside. Okay, spin, the idea of spin was there anyway. But he does this crazy thing. Dirac finds out that if there is an electron, there must be a positron. And he goes crazy when he discovered this. This is 1928. He writes this equation, realizes immediately. He takes 3 years of song and dance, all kinds of incredible things to finally say it. By the way, this is very interesting. There is a moral in this. I, for one, have a great nostalgia of this era in which I never lived. I lived, however, in the era for a while which kept some of this, how to say, responsibility. Notice how incredibly serious these people were. Why didn't Dirac say there was a positron? Because his life depending on that. You couldn't just say things that you do. As I'm talking to you, someone is sending a paper to the archive with 15 new particles and 35 new transformations and so on, or working in for whatever number of dimensions, saying that he's doing, or she, a simple extension. Here is a guy who is revolutionizing physics, but he's scared to say that there is this particle because if he's wrong, he's gonna be known as such. What you wrote, what you said mattered. He even said, by the way, he even said that E bar, a year or so later, he says it's a proton. He asked the question, which is crazy. And you know what he says? Because what he finds out, by the way, I should have written, ME must be equal to ME bar. And in the relativistic field theory, which has CPT, this of course is a consequence. He finds it. But how can positron be a proton? After all, M proton is 2,000 times M electron. Well, he says maybe we'll understand one day. Oppenheimer wrote a paper criticizing this because then proton and electron would annihilate. In 1931, Dirac says this. Finally, he takes the gut, says there is a particle, okay? So this, of course, is crazy. This cannot be true. Positron is just like the electron, only has an opposite charge, right? When Q of the electron is -1 in with our conventions, QE bar, as you and I know, is +1. By the way, you know, this is very interesting. In 1921, Chow at Caltech, a year or two before, I think it was 29 roughly, saw a positron. He was a graduate student, Chow. He was doing cosmic ray experiments, and what comes from the cosmic rays will be both electrons and positrons. And he finds out that there is a particle from the cosmic rays that moves in the opposite direction from the electron in the electric field. He's running around the corridors of Caltech telling everybody that he's seeing this incredible thing. He made two great mistakes, unforgivable. One, to tell everybody, but you're a graduate student, it's not easy, you understand. You don't really trust yourself as a graduate student. And then he made another even more grave mistake when they told him that he's stupid and he's something that cannot exist. Dirac didn't have the courage to say it. He didn't publish his findings. In 1931, Dirac says this. This is in 1931. And then immediately in 1932, there was a postdoc at Caltech, again called Anderson, always at Caltech. He repeated the experiment of Chow, and this guy got a Nobel Prize. This is one of the greatest ironies. I will not tell you so much about prizes. I will tell you when the prizes are not deserved, or when there is injustice. This one is one of the most crazy things in the world. The guy that discovered it before him disappeared in the dustbin of history. Well, he didn't publish. So this is a lesson for you young people. You will often make discoveries, quote unquote, which are completely wrong, and your advisor will show you that this is nonsense and so on. But sometimes you may be right. You know, it's very tricky when to listen to your advisor and whoever around and where not. Okay. So this little story is just to emphasize the importance. Okay, this is the beginning of particle physics, really. The fact that for every particle we have an opposite charge, antiparticle, if they carry charge. Like proton has an antiproton, and W plus has a W minus, and so on. Okay, antiparticles. That's the essence of modern particle physics, or particle physics in general. So charge conjugation, what is charge conjugation? It's the fact that the QED Lagrangian, Dirac Lagrangians is invariant under C, psi bar transpose. You see what it is. This is C, gamma 0, psi star. Since psi bar, I should have written before, of course, is psi dagger, gamma 0. But you know that. This is charge conjugation, and QED is invariant. That, of course, it's obvious. With particle going to antiparticle, you know that electron couples equally to the photon as the positron does, except for the charge. So you see, the wave function or the field goes into the complex conjugate, which changes the charge. Why? Because when phi goes as e to the I theta q phi, psi star goes into e to the minus I theta q phi, which is psi star, which is e to the I theta minus q psi star. So I could write like this, call it q. It will be clear in a second, where q acting on phi q is the charge. Small q is a number. So you see manifestly that if phi q has charge q, psi q star trivially has charge q star, minus q, not q star, I'm sorry, charge minus q. And that's what psi c is. The crucial thing is that why this what charge conjugation means that if psi transforms as psi, if it is a spinner, then psi c transforms into S psi c. It's also a spinner, where psi c is C psi bar transpose. See? This you know, right? Is there anybody who doesn't know this, who is not completely familiar with this? I have to know. You have to speak now, forever stay silent. Any of you that has some doubt, okay? I'm not teaching charge conjugation. I'm reminding you that there is charge conjugation. If you're unable to do this, you know, in a span of a few minutes, then you go, and when we have office hours, then you and I, we can go and remind ourselves of these basic things. I'm just going to ask you to rederive this if you haven't done it recently. Okay, so this is charge conjugation. What does it do? It's very important. Take this following spinner, UL0. It will go into what? Oh, I'm sorry. I forgot to define C. The thing is that C transpose is minus C. C gamma mu C transpose is minus gamma mu transpose. This is the definition of charge conjugation. Also, it will turn out C square is minus 1. This is needed to show, this is essential here, that of course psi and psi c transform the same way. Because of the transposal, you have to go from gamma mu to gamma mu transpose, and this is what charge conjugation does with the minus sign. I will use this charge conjugation. This is, you know, mine. This is Goran's charge conjugation. Size I gamma 2 gamma 0. It's easy to check that it has these properties. Basically everything can be derived without using a specific realization of charge conjugation, but we will use it just to be to simplify our lives. Okay. So what I want is I took psi, which was UL0, a purely left-handed fermion. What happens under psi c? Let's find it's I gamma 2 gamma 0 psi bar transpose, which is I gamma 2 gamma 0, another gamma 0 by definition, psi star, which is I gamma 2 gamma 0 square is 1, UL star 0. But remember gamma 2, let me write again, is 0, sigma 2 minus sigma 2, 0. So what is this? Is 0 minus I sigma 2 UL star. Notice what charge conjugation does. In other words, UL0 goes under charge conjugation into 0 minus I sigma 2 UL star. Of course, takes a particle into antiparticles. The wave function was UL, now it's UL star that has an opposite charge. But equally important, you and I will find out, is that charge conjugation is a left-right symmetry. Left-right operation, if you wish. It's a symmetry, so there is a left-right symmetry that I could call as much as parity. The mirror takes left to right and takes particle into antiparticle in the mirror. A left-handed particle, from now on, you will have to keep in mind, whether I talk about the right-handed electron, you know, now I'll have to talk in the future when I discuss weak interactions, I'll have to talk about the electron, not just as an electron, there are actually two of them, as you know, left and right. But I may speak of the left-handed electron. I may speak, so language that I can use. And language is very important. And, you know, doing physics well is choosing, you know, you have to find the right theories to start with. That's choosing your Lagrangian, your principle, your idea, whatever. Then you write the Lagrangian. Then you try to find the ground state. You need to know the ground state, of course, in quantum world. Then you have to use the right variables, also the right language to describe phenomena. Using the right language, by the way, is maybe one of the most essential things talked very little about. And there may be the crux that may lead you to a discovery if you use the right language. And the right language, for example, if I have a spin or psi, I may talk about psi L of psi R. That's a very useful language because it's telling me whether, you know, when I'm focused on parity, that's very useful. But I may also talk about psi L, about psi CL. It's completely equivalent, this language, to this one, because this is C, psi R bar transpose. Charge conjugation takes left and right. So I can work with psi L, here it is. I can work with psi R. This is once again C gamma 0 psi R star. I can work with psi R. I can also work with psi R star. It's a question of convention. It's for a complex number. What is that a number or Z star, right? So that I want you to remember forever. In the art of doing the weak interaction physics is the capacity to go from 4-component to 2-component left and right, but at the same time also the capacity to go from particle to antiparticle length. So in particular, if I have a left-handed electron, so if it is an electron, I will speak of a left-handed electron and a right-handed electron, left-right electrons. Or I may speak about the left-handed electron and the left-handed positron. So everybody's left here. Left electron plus left positron. This is why the Dirac wave function or the field that corresponds is 4-component, because it describes particle and antiparticle. That's even better way physically to remember. Okay, you say it describes left and right, but this is kind of mathematical statement. The physical statement is it has to describe particle and antiparticle, and therefore you have to double the degrees of freedom. Electron and positron are independent wave functions, okay, when it's at the same chirality. Or if you wish, EL and ER are independent. They have nothing to do with each other. They are connected through the mass term, but they are independent wave functions, completely. These are independent. Okay. What else? I'm waiting for a question. So in other words, QED, invariant under P or C. I should only to remind you, under C, A mu goes into minus A mu under C. It's a left-right symmetric theory. It's very interesting, completely left-right symmetric. Not a trace of violation. A mu goes into minus A mu. All right. That's what we have. What else I want to say here before I move on? I'm just thinking, you know, I want to start the standard model. This is not the standard model. This is pre-standard model, this is precursor. But I want to make sure that I've said everything. The questions would help. We still have a few more minutes. I'm not going to start anything new. Well, we had 20 minutes less. We had a little more time. We had another 15 minutes. Okay, something I may say. And by the way, what I mean here by the language, I'll be using both languages. Most of the time, I'll be using the left-right language. In the standard model weak interaction physics, I want to prepare you for beyond the standard model. If you, for example, liked supersymmetry, then you would use this particle antiparticle language, same chiralities happens. If you like to work on grand unification, you know, the idea to unify strong and weak interactions, you would again have to work with the same chirality fields. And so you would learn the other language, okay? But it's good to start kind of preparing ourselves for what is ahead. Most of the beyond the standard model physics, you need also the language of electron and positron. So I'll try from time to time to use both. Okay. What I forgot to say, and this is I should finish on before I move because I need to start about here. I have forgot to speak about gauge redundancy a little more. Again, something that you know. Gauge redundancy, the famous gauge freedom. I have a mu that transforms into a mu minus 1 over e d mu theta of x. And my Lagrangian of A is minus 1/4 f mu. And I want to describe physical processes a la Feynman. Sorry, I don't know why I draw it like this. Feynman tells me that everything is in the propagator. All the physics of the beauty of course, of Feynman approach is that what goes on is captured in a little diagram. Okay, this is mind-bogglingly useful. So I need to know the propagator, right? Here, the way the interaction goes is that there is a propagator. Or the photon propagates between the fermion number 1 and fermion number 2. There are two fermions scattering on each other. And therefore, I need a propagator. Now, what is the propagator? As you know, that's the inverse, among other things, of the quadratic form. In LA, in the Maxwell-Lagrangian. What is the inverse of this f mu nu, f mu nu? Who can tell me? After all, I can write like this. It's anti-symmetric, so I'll write like this. I could integrate this by part. Well, it is minus a half d mu a nu, d nu a mu, d mu a nu, plus 1/2 d mu a nu, d nu a mu. No, I don't want this. Or maybe I can. If I am tricky, d nu a mu. No. When you're wrong, but I can correct it here if I want. I can write any which way as long as I'm summing lower and upper indices. I can integrate this by parts. So this is plus 1/2. The box a nu, box a nu, minus, now it becomes 1/2 A nu, d mu, d nu, A nu. I can go to momentum space. Oh, maybe I can write it just a little more elegantly. I'm sorry. I can write this as 1/2 A mu box G mu nu minus d mu d nu A nu, as you know, so that in the momentum space, this is what you and I want to do anyway. I do Fourier transform, or I just write the particular component. A mu is e to the I p times x epsilon mu. P times q, p times x. What am I writing? Just looking at the mode with momentum p, I will get 1/2 or minus 1/2 epsilon mu p square g mu nu minus p mu p nu epsilon nu. So I'm asking you, okay, you all know this, right? It seems you're not gonna ask me here, this is trivial. Well, anyway, I just derived it. What is the inverse of this?
Feynman propagator for photon.
You know the form of it to tell me?
I over k p square minus plus I epsilon.
Well, forget I epsilon. That's a subtlety. That you're saying I over p square.
Yes.
Impossible. Inverse means that I multiply this by this. So you're saying this is the inverse. I will call it d. Well, I will call it delta. The normalization is not so important. We'll worry about the signs. So the delta mu. You meant here maybe g mu nu. You didn't tell me what the tensor index is. What should I put here? What index? I have to put some index here. G mu nu. Should I write this?
Yes.
Well, that means that this times the piece here should give me 1. Or some delta function. Impossible.
Yeah, we need the gauge fixing
Oh, yes.
because it has.
Right, because there is no inverse.
There is no inverse. Yes.
Thank you. No inverse. And it's very easy to see because this guy is a projector. If you write g mu nu minus p nu over p square, I don't know how we would write that. Okay, I could call this some p mu nu. Then you will find out that p mu nu p nu alpha is delta is equal to itself. P square is p. Sorry, is p mu alpha. It's a projector. P square is p, has no inverse. It's easy to see. Projectors have no inverse. Why? Because I'm trying to work with all 4 components, but they are not physical. It cannot be like this, right? I need a gauge fixing. There are many ways of fixing the gauge. I have to arrive at the 2 components. The most elegant is that you write to QED, so gauge fixing. One that is really useful is to add the gauge fixing term, which is minus 1 over 2 psi. We use this sign, d mu, a mu square. You write something that manifestly breaks this redundancy. There is no more gauge symmetry, gauge redundancy here. And I introduce this parameter C because, of course, the theory, this is just a way of computing, right? The physical results are, of course, gauge invariant. The theory is gauge invariant to start with. But in order to compute, I have to break this redundancy. You know, it's like kind of using Lagrange multiplier or something, because just to compute it. And C is very nice because the physics, okay, there should be no dependence. So I have a check, no dependence on C. This is the requirement. This means that you have a physical theory. As much as it has to be Lorentz invariant, it has to correspond to the original symmetry of the Lagrangian. Okay, now I can do the inverse. And whether I will do it as a homework, I'm not sure. You're supposed to know that. If someone knows the value of the propagator, now there is an inverse. I've broken this spell of this being a projector by adding a psi piece. It has the following form. There is a convention here that is worth mentioning, 1 over p squared. Someone maybe knows there is G mu nu, but not just the G mu nu, also something else. Well, there will be also p mu over p squared. Someone knows the coefficient here?
Psi.
Psi minus 1.
Derive. Please derive if you don't. It's very easy. And actually there are some gauges which are well known. Psi 1 is equal 1 is called Feynman. Feynman used to like. By the way, that's the best gauge to use if you trust yourself. You have to be very good. You know, there are people who actually keep psi because they are not sure if they're making a mistake. And keeping psi has an advantage that in the end, it has to cancel, but it's hard to compute. And then there was an interesting gauge, which is called the transverse gauge or Landau gauge. Landau used to have this gauge. Sometimes it can be useful. Psi equals 0, okay. This is what we these are two things that we need to do in order to do our computations. We have to identify the Lagrangian. We have the vacuum. The vacuum of QED is very easy. In the vacuum, the value of these fields, psi is 0. Vacuum is actually empty, and A mu is 0. You're not taking any particular values, thank God, because this will break Lorentz symmetry, either rotations or boosts or bows. By the way, when we use certain symmetries like Lorentz symmetries, we could be wrong in principle. I'm gonna pretend in the rest of the course that Lorentz symmetry is exact because I don't know how to work. If I open that Pandora box, I will go crazy, okay? Because I couldn't even organize my knowledge. There are people who work on that. And that's an endless childish game because you have infinitely many ways of breaking the Lorentz symmetry. And you can write, of course, infinitely many papers if you like to do that. So there will be certain symmetries I'm going to take as sacred. I will also work with the electromagnetic gauge invariance and the massless photon, although tomorrow photon may be massive. Okay, I'll be coming back to these issues. Okay, you can always challenging me why I will take some symmetries as sacred. Most of the time is when I don't know how to formulate my theory without them. I wouldn't know how to work with a broken charge invariance. There is no QED formulation with broken charge invariance, explicit, or Lorentz invariance. There is no workable theory. And so if I have a particle 1 with a momentum P1 and the momentum P2, exchange momentum is say P2 minus P1. Sorry, not P2 minus P1, I don't want that. I have a momentum P1 becoming P1 prime. I have a momentum here, Q exchange. The Q would be P1 prime minus P1 equal P2 minus P2 prime, whatever. You know what I mean by that. The propagator, the photon propagator is, now it is true what you told me, it's proportional to 1 over Q squared. Which was 1 over P squared, the way I call it. I can pretend like Feynman to take psi equal. Psi will cancel anyway. It's of the order 1 over Q squared. So you see, this is a measure of the strength. the Q tells me, which is, you know, the inverse of the distance, okay? You know, energy, the space-time connection, okay? The momentum, distance, and so on. The Q is corresponds to 1 over the distance, and of course the distance measures the strength. The Fourier transform is 1 over Q square is 1 over R, as you know. And this will be very important when we introduce the weak interactions. Tomorrow, we have a lecture tomorrow, am I right?
Yes.
Okay, good, sorry. Just to remind you, the course unfortunately had to be accelerated, okay? It's gonna be maybe a little hard for you guys to follow. The advantage, however, will be that, you know, the thing will stick because we'll be chewing on the same thing in continuation. The harder part will be to have time to catch up. So I strongly urge you to ask questions, to stop me. I could really, I could stop here. Maybe I forgot to say something. I teach without notes, so sometimes I forget. Okay, I can't show you. I could show you if I was teaching on the blackboard. I like this to be developed as to makes me reflect and think and to make you participate. But I'm thinking whether I have something to say. You can think whether I have something to ask. Hopefully the questions are there, because we're not there because you know this. Now let's check the thing about if you wrote on the chat. Where is the chat? Why don't I see the chat? Because I'm not the host? No, I don't understand. Oh no, sorry. I'm very absent-minded. Let's go on the chat. We have on Thursday afternoon, only other afternoon weekdays are free. 9 a.m. someone says no. That's I don't show up. You know, it's already a struggle. I normally teach after lunch. It's always an experiment when I teach 11. I was the last. I'm a late riser. I'm sorry. There's some advantages and disadvantages when you become well known. So you may become infamous. Even my conference talks are in the afternoon. Most people know I just can't give talks in the morning. So okay, then I will think. I think Wednesday could be. Thursday. Wednesday seems to be. It should be in the middle of the week. Seems to me best. You could offer your opinion. It could be Wednesday or Friday. Do you have any preference? No, Friday I have something else. No, Wednesday would be good, so that something accumulates. Thursday you have. What time is the GR tutorial on Thursday? In case I had to do Thursday.
4 p.m.
4 p.m. So in principle we could meet at 2, but it would be better maybe that's in another afternoon. People would prefer it to be. Say on Wednesdays rather than Thursdays. You can just speak.
I think Wednesday is good.
Wednesday is good?
Yeah.
Everybody happy with the Wednesday? Okay. Very good. By the way, because sometimes you don't, the advantages of these office hours when you come together, you hear each other asking questions and it may help you. When I do that, when I was just, as I told you, I'm spending a lot of time in LMU in Germany, I'm teaching there. And I found out that